Hey everyone, so I thought I'd help you guys out with some of the WebAssign. I know we did the lesson, but some of these circuits do look kind of crazy, and I don't want you to get panicked about this. I want to make it easier. First thing is, you know my numbers are going to be different. I'm not really going to focus on numbers so much, just try to give you a general setup. 18 and 19 just ask you to solve for resistance, the total or equivalent they call it. They don't ask you to solve for current or voltages, but 20 and 21 will do that. So just to help you out, I think 18 will kind of trick you out, but Graham actually said this in class today. It was kind of cool what he was talking about if you didn't catch on. If you look at 18's diagram right now, R, the blank one, for me it's 12 ohms and it'll be different for you, but you know every resistance. It is a combination though because you do have series and parallel. Now for this one, the trick is 18 ohm, 9 ohm, and 6 ohm, those resistors, they are right after the first junction if you follow conventional current, and they are actually the only resistors on their own path before the closing junction. So all three of those actually are in parallel with one another. So I know I said look for pairs like two that have a relationship, but as Graham said, sometimes you guys might actually have three that are in series, or in this case, three that are in parallel. So if you want to do the inverse equation for all three of those and find the common denominator, awesome. That'll just eliminate one more step for you. Once you then simplify that down to then the equivalent resistance for those three, then if you do the drawing, which you should, especially for the next questions, 20 and 21, if you do the drawing, it's pretty obvious what the last relationship is, okay? All right, so I'm not going to do the work for that. 20, just a heads up, I kind of did one identical to this, so if you follow our example, that should be a gimme question. And then 21, just to avoid chaos during office hours, which I still want you guys to come in, definitely come in if you need some help. But 21 is kind of a tricky looking one. It doesn't look like the one I did, of course, and I don't want you to panic. So I'm going to switch over. So that's the question. I'm not going to focus on numbers because I know yours are different. I'm going to focus over or switch over to camera though. And see my puzzle there? How cool is that? I need more puzzles though. They're all sold out now. All right. I guess I can just actually do photo. So let me zoom in a little more. All right. So I'm just, without numbers, I'm going to show you the simplification, kind of give you the cheat for it, okay? Because if it goes wrong at the beginning, then it's just a nightmare altogether. All right, so pretty quick. And I hope I'm still recording. Yeah, I'm still recording. All right, so really quick, this one, we're going to try to find the two that have a relationship without anything else interfering. The common mistake is that people will go around and let's say they went this way, opposite of conventional current. They'll be like, oh, R3 and R2? Well, if I just go on this inside loop, they're on their own path. So some people will say that's in series. That's not, though, because there's actually a junction in between them. And if there's a junction, they're not in series because there's not just one path between their connection. There is then a second. So try to avoid that mistake. The first combination that I see actually, which other people also might be like, well, I guess if there's two different paths, they're in parallel then. That's again another issue because parallel is a junction before these two are on their own path and after. So I don't see a junction before this. So the first combination, which I think is kind of easy to see, hopefully after our lesson, is resistor 4 and resistor 1. Because once I get onto this individual path, let's go conventional current. All right, even though current splits right here, once I get onto this individual path, these are the only two on this path, and again, there's no junction between them. So since there's just one isolated path, I know these are in series. So first thing we need to do is find that combination, which series is adding them up. I'm not going to, again, do the math, but once you do the math, you would then redraw the picture and basically say this is the equivalent resistant for resistors 1 and 4. I know on WebAssign it's not called 4, I just did that to simplify it. And then keep the resistors that were still there that we didn't do anything to. Sorry, I put that over there. All right, then we just continue the process. So again, we simplified series first. All right, next one. Again, be a little cautious about a series connection because when you see these, there is still a junction in between, so I still can't do anything with this. And the other thing is some people look at this and they think all three of these are in parallel. They're not, because again, the rule is to be in parallel, you have to have a junction before all of them, if you are trying to do all three, and then a junction after, which if I follow conventional, sure, there's a junction here, but then this junction closes before I even get to resistor 3. So this resistor, it's not in parallel with these other two. All right. If it were, it would actually start its own path probably up here after the first junction, be right around here, and then have a junction after it down here. Okay. So we can't still can't do anything with R3, so it's going to be a combination of these two, and you got it. They're each on their own path after this junction and before this junction, and they are the only resistors on their own path, so they are in parallel. So remember when you solve for parallel, it's not the sum, it's the reciprocal equation, so be cautious with that. But then when I redo the drawing, I'm then going to have, once I do the combination of these two values, I'm then going to have an equivalent resistor for all three actually. Resistor 1 and 4, and now 2. So you kind of continue the math from what you did here down to here. All right. Then all that's left is resistor 3 and the battery. And I think when you always get to the second to last picture, it's pretty easy to tell what connection it's in. Finally, resistor 3 is now on a single path with the other ones. So this would then take me to the total by means of a series connection. So when I get to the last one, I don't really care where you put it. I typically call it total because you then know you're at the end, but you'll see WebAssign, they call it equivalent, which is okay too. All right, but I could solve for that then by just adding these up because it's in series. All right. When you go to then tackle the currents and voltages, these pictures are so important because remember, once you get down here, you can solve for VT, IT, and you should of course have RT. And I shouldn't really say you should solve for VT because it was given 12 volts. All right. But now that you have the total resistance going through these steps, you can then solve for total current. And then remember, you can take one of these two values backwards and apply it to both of these. Which one depends upon what type of relationship they're in. So use the video if you forgot that in our notes from earlier, but I hope this helps out a lot, guys. Remember, if you want to come into office hours still on Friday, definitely come in and I'll help you out with whatever you need, all right? Good luck on these, guys.